Mass is the way we measure the amount of matter that's present. That's true with macroscale things. That's also true of atoms. So let's take a look at atomic masses. Now, first of all, atoms have extremely small masses because they are extremely small. So it's convenient for us to use a mass unit that's also extremely small. The mass unit that we tend to use is something called an atomic mass unit, or AMU, or sometimes just U as an abbreviation there. Makes sense? An atomic mass unit is defined as 1/12 the mass of a carbon atom that has a mass number of 12. So a mass number of 12 means it's 6 protons and 6 neutrons. Well, carbon means it's 6 protons. A mass number of 12 means it's 6 protons and 6 neutrons. An atom means that it's 6 electrons to balance the charge of the 6 protons. When we're looking at masses of individual subatomic particles, protons and neutrons have masses that are very close to 1 AMU. So when we look at the mass of an atom, we'll find that it's very often very close to the mass number of an atom. But remember, mass is not mass number, and mass number is not mass. They're two slightly different things. When we're talking about elements, often elements exist as more than one stable isotope. And because of that, the way we calculate the average atomic mass is by using something called a weighted average. Now, people always get a little anxious, a little nervous when we start talking about atoms and weighted average. But really, you know how to do weighted averages. Just because we're talking about them in a chemistry context doesn't mean that they're different or harder. They're the same thing that you already know how to do. So let's take a look at an example so I can prove to you that you know how to do weighted averages. Let's start simple. An orange has a mass of 200 grams, an apple has a mass of 90 grams. If you have one apple and one orange in a bag, what is the average mass of a piece of fruit in the bag? Well, you could do this one without me showing you, but I've got one apple at 90 grams, and notice the decimal here, so I've got proper sig figs. I've got one orange at 200 grams. That gives me, what, 290 total grams of fruit. And I've got two pieces of fruit in the bag. So 290 divided by 2 is 145, 3 sig figs in this result. Well, that's fine. That's one apple and one orange. But we usually don't deal with one type of atom or one isotope, one atom of an isotope and another atom of an isotope. We're usually dealing with a little bit bigger amounts than this. So let's make this just a little bit more interesting. Let's take that same apple and orange, and let's say we've got 7 apples in our bag and 3 oranges in our bag. So what's the average mass of a piece of fruit in the bag? Well, 7 apples times 90 grams plus 3 oranges times 200 grams divided by a total of 10 pieces of fruit gives me an average mass of 123 grams per fruit. Now, just as a quick little note, notice that this is less than the 1-to-1 mix, but what do we have? We've got 7 apples and 3 oranges. We've got more of the lighter item, so we would expect this to be closer to the mass of the lighter item than when we have an equal mixture 1-to-1 of those. This is a weighted average. We took into account the fact that we don't have the same number of each type of piece. So, apples and oranges. Let's extend this a little bit farther. What if we've got a truck full of fruit instead of a bag full of fruit? Well, what if 70% of those apples, now instead of 7, let's call it 70%, of those fruits are apples, and 30% of those fruits are oranges. What's the average mass of a piece of fruit in the truck? Well, 70% apple times 90 grams plus 30% oranges times 200 grams divided by 100%, that's all the fruit, gives us It gives us 123 grams per fruit. It's exactly the same as the previous problem because this is still a 7-to-3 ratio, just like in the previous one where we only had 7 and 3 pieces. Now we've got 70% and 30% because percents are relative numbers, and we're taking relative weighted averages here. So, do you believe me? You know how to do weighted averages. What if we make that into a chemistry problem? A certain element has two isotopes that have masses of 118.413 AMU and 121.0618 AMU. The heavier isotope is found to be 63.19% abundant. What's the average atomic mass of this element? So a few things here. First of all, I only gave you the percent of one of them because if it only has two, certain element has two isotopes, then whatever the rest of it is to get up to 100% is how much we've got of that. So let's start putting it together the same way we did the previous problem. 63.19% times 121.0618, that's our AMU of the heavier isotope, plus 36.81, that's the rest to get us up to 100%, times 118.4138 AMU divided by 100 gives us 120.09 AMU. It's the apples and oranges problem. It's just using isotopes of an element. Now, as a little bit of a double check, the heavier isotope is more abundant. There's more of that. So our answer should be closer to the heavier mass than the lighter mass, and in this case it is. That's a convenient way for you to kind of check yourself on some of these problems. So that's really the problem. Now, as an added little piece here, since we're all still kind of getting accustomed to significant figures, let's take a moment to very specifically and explicitly look at significant figures on this specific problem. When we're doing significant figures on a multi-step problem like this, a multi-part mixed operation problem, just work through it the way you do the math. Work through it step by step. So first, we're going to multiply each term in the top. So 63.19 times 121.0618 is 7,649. The rest of that number. 36.81 times 118.4138 is that number. Now, in here, I'm not rounding these off at this point. Don't round multiple times, and especially don't round early in your process. Carry all of your numbers through and round at the end. But I did designate in both of these numbers with a little green bolded number where my uncertainty lies. If I were going to round this number using sig fig rules, this is where I'd round it. I have 4 sig figs going in and 3, 6, 7 sig figs. So multiplying those, my result should have the same number of sig figs as the smaller sig fig number. So I should have rounded it there if I were reporting this number. Same thing over here, 4 sig figs. I would round it there if I were rounding and reporting this number, but I'm not. So let's keep those numbers, those big, ugly, full calculator numbers in there. Now let's add these together. If I add these two terms together, I get 12,008.70712 as a result. And again, I've kept track of my sig fig. Now that I'm adding, I'm going to round to the same digit as my least precise number. So the shortest decimal. These are both sig figs. These are both uncertain in the ones position. So if I were to report this, I would be rounding this number at the ones position, but I'm not. So let's do the next math step. And the next math step, this is one of those definitional numbers, right? 100%. I'm talking about all of something. So this is a definitional number. This is exactly 100% is all of my sample. So this is not going to limit my sig figs, which means that after I divide by 100, that 8 is still my sig fig digit, and if I round to that sig fig digit, I get 120.09 AMU, 5 sig figs in my result. Look at weighted averages. You know how to do them. You've done them before, whether you realize it or not. And just work through the math, and good luck on those sig figs as well. They're not that hard. They just take a little bit of deliberate practice working through a few of them. So see you next time.